Hello, everybody. Welcome back to the Econ Playground. Today, we got a bigger group with us. Tegan and Caleb, who have been on many times before, and Matt, who was with us a few months ago, and then a special guest, David Shera, who's my dad. So, and what we're going to talk about is this book, Gödel, Escher, Bach, which is very famous. I think it's probably the only like mathematical book or like book of this type that has won the Pulitzer Prize, just because that's very rare for someone with the talent, the kind of like talent as a writer and as an entertainer to write about this kind of topic material. But it's something I think we've had it in our basement for like years, and it's one of those books that I would always see on the shelf and be like, oh, that's that book that I have no idea what it's about, but now we're reading it. So we're going to read it in, I guess, 6 parts about over the next few weeks and talk about it. And it's about mathematics and music and art and everything. It's about thought. So if a book is about thought, it's literally about everything in a way. Anything that you can think about. It's about all thinkable things, which we're going to talk about. What counts as a thinkable thing? What makes something thinkable? We're probably going to get into that. And then, but yeah, anyway, anybody have any first impressions or first thoughts about the book?
I guess I could start. It's reading faster than I thought. I thought it was very dense and so it looked kind of ominous, but it's not too bad. It does, like you said, it's in a narrative form, so it kind of goes through things pretty quickly, and that's good. It's also been faster for me because I studied mathematics, so I'm kind of already familiar with a lot of the terms and concepts.
I feel like I was struck by that too. I had the same impression of I've always sort of heard or thought that this is a very dense book, and it is dense with content, but agreed, like their narrative structure that he kind of takes on really makes it a much smoother read than I was expecting. At least at the outset of the stage we're at with it.
Yeah, you'll like read whole sections and you'll be like, I feel like I missed something, because there's, that there's so much and you're like, I have to have like missed something, or I have to misunderstand it. But he's really just taking like 10 pages to give you like, oh, I just taught you addition, which you already knew, but you didn't know that you really knew. So, and he'll do this proof and I'm like, there's no way I understood that. And then I'll like do it on the paper and I'm like, I do, I get it. But it's just, each chapter is just like a small bite-sized thing that's turning into a massive endeavor. So yeah, it's fantastic.
I'm absolutely loving his illustrations from art and music. I think that's by far the most interesting part for me so far, is you really get a vision of what he's talking about in mathematics when you see the strange loops in the Escher paintings, or really, especially for me, I'm very interested in Bach. I took one class on Bach in particular in undergrad. That was awesome, and it's so interesting to hear him talking about it and then see these it's not so much an application, but rather just an analog, the analog to mathematical recursiveness that you find in music.
Yeah, and it's also a very engaging book. So he's got like the illustrations you're interacting with this, but then he also sets up thought puzzles that you work out, and so you're working out these theorems from axioms and rule sets that he gives you. So it's very good at capturing your attention and making you actually learn by practicing the things that he's talking about. They're also like very interesting puzzles to work out too. So it's not like you just want to skip over it and then just do the rest of the reading. You actually stop and you go like, how am I going to do this? And you start figuring stuff out. So it's a lot of fun to read so far.
Sort of an interactive, not really like a choose your own adventure novel, but very engaging in that way, Caleb.
Yeah, and Tegan, you were talking about the visuals, how useful the visuals are. It's very, very much like if you take like a math class and you spend the first, like an advanced math class, the first few weeks you do like truth tables, you learn like logical rules. This is like the intro math class. And then But then they're like, oh, by the way, you can do like a Venn diagram and like P and Q and then like see it all. And you see all of the different things like in black and white. So when he drew, I've kind of understood some of the stuff about Gödel's proof before, or Gödel's theorem before, but the illustration that he has on page 71, this is of the 20th anniversary edition, with the two trees where the white representing like theorems, like things that are true within this system, and black representing things that are false. Yeah, exactly that one. And like that, it's like that totally visualizes it perfectly, and you get this tree-like structure, like a white tree and a dark tree, and you're like, what what is that? That feels like the mythological almost that he's like bringing up, you know, like the two trees in the Silmarillion. Yeah,
I love how your first mythical tree you go to is the Silmarillion and not like Din or something.
Not Genesis. Yeah.
Oh yeah, true. Yeah, but you know, in some interpretations, it's all floating around. But yeah, I really like that diagram because it like brought it home to me, and it reminded me of yeah, how things are normally represented in math classes.
Totally. It's a very concise, I mean, not concise. I'm it's sort of the opposite. It's kind of free ranging. It's very playful. And he has a lot of, you know, he seems to be able to kind of reference, you know, artistic thinkers, artists, and sort of be like what he's seeing in these Escher drawings is often kind of paralleling or mirroring you know, what you know, points he's making about active and passive meaning that we project onto you know, these formal proof systems. Anyway, it's just it's kind of difficult to convey, but he does such a good job of conveying these ideas in a playful way. Yeah.
What exactly did active and passive mean? Because I missed, he used a lot of different like this and that terms, but I didn't catch that one precisely.
Like there were probably a few other terms that and that's another helpful thing is, you know, he's italicizing sort of key terms as he goes, which is helpful to me. But I think that if I can try to find the spot where he brings up active and passive, there's an example he has, right, that so he's got the PQ system, and there's this example he states of it would be because you've like comprehended the meaning of this of this formal system to be having to do with addition, that it's then tempting to come up with new statements in P's and Q's and hyphens, which maybe I'm not giving the reader enough. Maybe we can kind of go back and give the reader a little more context, but or the listener. But it's tempting to come up with statements like he does on page 52, where you've got P plus, or excuse me, like some amalgam of dashes plus another dash plus another dash, and it's tempting to be able to say that you could say that, but you really can't say that with the formal proof system. It's just that the isomorphism that you've noticed in addition, where you usually can say this plus that plus this, you can sort of repeatedly add things, but you can't do that. That's sort of something that you're projecting onto the system, but it's not really a rule that's set up as an axiom or a rule of inference. So I think I'm doing a poor job of explaining this, but I think he sort of says that in a formal proof system, the meaning must remain passive. We can read each string according to the meaning of its constituent symbols, but we do not have the right to create new theorems purely based on the meaning we've assigned to the symbols or the interpretation we've brought to it. Maybe somebody else can elaborate.
Right. Yeah, it's because even having three things added together won't work in this system. It only adds two things together and gets an answer. You can't go to three things, even though it works and it makes sense. It's isomorphic to addition. It doesn't have a rule for adding three things together. Only two. And so there is something outside the system, so outside what can be done by the rules and the theorems. Yeah, the system. outside the system.
You would
itself.
need the PPQ system, and then it wouldn't be the PQ system anymore.
You're right,
Yeah.
right,
Yeah.
exactly.
Yeah. So he's kind of like warning you of having the system and then seeing the isomorphism with an outside meaning, but then projecting that outside meaning back into the formal system in such a way that subverts the rules of the formal system.
I don't know if he's getting at this in the book, but that, there are these things in algebra that come up the same way. For instance, you can't solve all polynomials within the real number system. Eventually you have to go outside and do imaginary numbers. And in fact, from what I learned when I was in mathematics, there's something beyond that. There's actually a polynomial, or there's probably a lot of them, polynomial in complex numbers that can't be solved in the complex number plane. So then you have to go to another level of something. That's called Galois theory. And so there's always, even though you start with something simple, usually it can get very complex very quickly.
Are those numbers, so there's reals is a subset of complex, right?
Right.
And then, so complex is a subset of Galois.
Well, yeah,
like
Galois was the person who kind of proved that this can always happen, that within any algebraic system is what he was working with. You can always find an equation that can't be solved within the system. So you have to go outside, create something new. And I guess that's not really needed much, so people don't go to that next level, at least not yet, that much.
Maybe it would be necessary for like quantum physics or something.
Something like that, yes.
Yeah, like I think it's that the complex numbers are like I think the term is like closed under algebra, which might not be the precise way to put that. I might be obscuring that, but
right.
But the idea is like for this set of statements to determine if they're true or false, you would have, well, actually not really, to determine solutions to these like questions, these certain set of questions, you need another set of like there's another sort of expansion of the field you have to go to. I don't know, I'm actually totally butchering that terminology right now, but the point I wanted to make is that like complex numbers appear very like abstract, but they really are very useful in like in a lot of applications. Like engineers use them for in like electrical engineering. I think like if you're if I haven't studied circuitry or much at all, but I think that for some of those some of the problems that they face there, they need to have complex numbers in order to solve them. So they're both useful and like abstract, and were arrived at through purely like abstract thinking.
That's true, and actually maybe a bit of an accident that it just so happened that one of the mathematicians started calling I the imaginary number, and not that it's particularly imaginary or anything, it's just they didn't know what else to call it, so it got this name, the imaginary number. So it seems like it must be not real or something. And so the names that have been attached to these mathematical concepts kind of have something to do with the real world, but they don't necessarily have that. It's kind of an accident. If you want to know, the usual way I think of it is if it involves I, it involves some kind of rotation. So if you take a matrix, you get the eigenvalues. If the eigenvalues are real, that has to do with expansion and contraction. And if they're imaginary, it has to do with rotation. So rotation is really just the imaginary part of the whatever transformation you're making. The rotation is the imaginary part.
So
I took a.
Go ahead, Tegan.
No, sorry, were you finished?
Yeah, go ahead.
Oh, okay. Yeah, I was just gonna say I took a differential equations course with my brother who's doing electrical engineering. And one of the most fascinating things that happened there related to imaginary numbers is when you're trying to do differential equations for sine and cosine functions, very often what happens is you end up with expressions that contain imaginary numbers, but that can be reduced to an expression on the what is it, real number plane? Yeah, that can be reduced to real numbers through an expansion of an infinite sum, which was just the most specifically, it expands into a sine or cosine thing on the real plane, which was just absolutely mind-blowing.
So again, one thing that I don't understand is so are you saying that in mathematics real is kind of conventionally defined, like once they, like the numbers at one point that they needed, they thought like this is a sufficient number of numbers, it like that?
It's called the real line, the line of real numbers, but I don't know what makes it more real than anything else. Numbers themselves are really just concepts, right?
Mm-hmm.
So it's kind of a conventional name, real numbers.
Sort of like prior to, I mean, like my impression is that in the 19th century and even into the early 20th century, but I think by the 19th century it was kind of mostly been settled, but there was a lot of work done to justify the idea that you could, really work with an idea like real numbers, that what really are the rules by which, what are the valid rules for, talking about and making statements about real numbers, was actually kind of like hard fought, battleground as well. I mean, back to like Pythagoras. I mean, he things like irrational numbers really bugged him. He thought that the idea that you could have a number that couldn't be expressed as a fraction of two natural numbers would be, so things like the square root of 2, or numbers like that, bugged the heck out of him and didn't quite fit neatly into a purely like Greek geometric interpretation of numbers. And for, so like natural numbers to irrational numbers to to real numbers, but there are a lot of numbers like pi, for instance, in the set of real numbers that are very like difficult to define, because, well, anyway, it's kind of, yeah, I think, go ahead, David.
No, go ahead. I
Like,
was thinking the pi is not one of the algebraic numbers. Like square root of 2 is an algebraic number, but pi is not. I guess neither is e, for that fact. But they're very important.
totally.
I get then on at the meta level, and going back to what he's talking about in the introduction, is why would something like that bother Pythagoras? Like, what was Pythagoras trying to do such that square root of 2 got in the way, right? Or was it just something because there was a reason that someone postulated it, like that I believe there was a particular set of problems they were working with where square root of 2 seemed to be an answer, but he refused that as an answer. So what is he defending by refusing square root of 2 as an answer? And then in the similar way, what was Hilbert and what's their names, Russell and Whitehead, what were they trying to defend by resisting or trying to complete an axiomatic version of mathematics that Gödel ended up shattering?
Yeah, so I think like all the way back to like Pythagoras and the problem that he's having with the square root of 2, there's a certain like natural intuition that we can very easily have with like natural numbers. So like positive whole number integers and stuff. And so you can kind of very easily conceptualize that in your mind. And then once you start adding in 0, negative numbers, like irrational numbers, it becomes harder and harder for like our intuition to grasp it. And once you get to the point of something like imaginary numbers, there's really nothing that we experience in our day-to-day lives where we can grab onto like some experience and tie our intuition with that experience to our like conceptualization of that kind of number, that kind of math that you're doing at that point. And so it's abstracted so far away from reality, and it still has use and applicability on reality, but it's so much harder to conceptualize and to tie something intuitively to I or to negative numbers or to irrational numbers than it is for whole number integers, positive whole number integers. So I think that's like one of the barriers you face.
So it's
And I
difficult.
also,
Go ahead, Caleb.
No, you go ahead.
Tegan. I just get like, it's like in the language that I'm seeing in some of this book, like it's difficult to identify an isomorphism for some of these systems. But they're often are there.
Oh yeah, Caleb had to run. He had to do something. But yeah, I was thinking too. It's kind of it's like if Pythagoras was in a position where he thought that he had understood everything, there's always this thing at the edge that's bugging him. Like, well, I discovered this system that explains everything, but then square root of 2 comes up and like is like the kid in The Emperor Has No Clothes is like, oh, you actually don't understand me, and my presence makes everyone know that you're naked, right? When I'm the one calling you out. Just like so, and Gödel is basically saying that's true for all mathematicians forever. So given that he's correct, right? So Gödel has some version of understanding, but not, he has something, but it's not the same kind of I know everything, right? All right, I'm prepared to face any mathematical problem, which is like the goal of people before him.
I kind of remember it being called good news and bad news. The bad news is you can never know everything, but the good news is there's always something to be researching, because you cannot know if you don't know a certain thing. Like you can't know a theorem is proven until it's proven. There's always something to work on. There's always more questions in science.
So Gödel basically proved job security for mathematicians for all the
and scientists also, I think.
Yeah.
Anyone who works with a formal system.
Yeah.
Economists, maybe, perhaps.
Yeah, economists for sure.
Linguists as well, perhaps.
Ooh, yeah.
Yeah. I was wondering about that with Gödel's theorem and economics. If I think that we'll have to read more of the book, and we'll probably talk about this later, because in economics there's an axiom system for rationality of it, like, behavior or a utility function has to meet certain criteria to be considered rational, or your choices need to be ordered in the same way as this utility function in order to be rational. And I was wondering whether or not you could propose something like propose a situation where it's unable to tell based on the response whether or not it's a rational response according to those axioms. But I think that that's not the case. I think that might be a complete system. I'm not sure though, based on the kinds of question it's asking.
I could speak to that a little bit. I mean, just if you so typically, right, in economics, the primitives are going to have to do with like objects that you have preferences over, and defining a preference relation is basically analogous to like the rules that you put onto a preference relation. Conditions that it satisfies will kind of tell you if it can be said to be rational, but those are basically going to be transitivity and completeness, which is very analogous to like any other like metric that you would place onto a onto a space. So I mean, the rule that like 3 is greater than 2 and 4 is greater than 3, so therefore 4 is greater than 2. A is greater than A is greater than B is greater than C, therefore A is greater than C. And the idea that any two objects will stand in relation to each other in some way. Okay, so hang on. I had so those being sort of the primitives of that, if you had a set of preferences that could be represented with a utility function, right? And you're going to maximize that utility function. You're going to basically be finding the roots of some equation to do that, like a Lagrangian or something, if you have a constraint in there. So we're just saying this guy is optimizing. And if we can represent that optimization, the objective function with a utility function. And just one thing to say is that, like, if some of the zeros, if some of the roots of that of the equation that you'll solve, maybe some of those roots are complex, right? You have a function, you're maximizing it, you're gonna then say you're gonna set some equation equal to 0 and see what answers, what control variables will satisfy that. And if it turns out that some of those answers are complex numbers, then, you know, I'm not sure whether I could say, like, right now whether it could be like an incomplete or a complete system or whatever, but at the very least you'll have some answer to the system that's very difficult to interpret, especially difficult to interpret, like if you're trying to find an isomorphism with, like, things that people actually consume or decisions that people actually make.
And then if that's the isomorphism that we're going for, then it might be difficult to find every single thing that people do and then interpret it back into the system. Like something that Tegan and I talk about is choice in beliefs. When you decide to believe something or decide to go down a certain path, it's unclear whether that can be read back into the system. And usually what economists will say, like, oh, well, given that they have, you know, this set of potential states they think the world can be in, and then a probability distribution over those states, then our system works out, but only given those things. So if economics can't understand how people get to that point where they say the world can be in A, B, or C, and then put those into probability buckets, then there's a limit to what economics can do, even in explaining basic human behavior, right?
I think you're going to come to a place where, for instance, when you're talking about maximizing a utility function, I think you're looking at a function that's well defined and doesn't have some kooky little backdoor thing to it. And for most real world situations, that's going to be the case. You might be able to make up a pathological utility function, but it would never be practical. I know there's certain other examples, like covariance matrices are always positive semi-definite. You're not going to get, so when you get the eigenvalues of a covariance matrix, it's always real numbers or zeros. You're not going to get that. So yeah, depending on your situation, maybe some things can be a closed system.
You know, like at the beginning of every economics textbook, when they're teaching you the indifference curves and stuff like that, usually they have all the axioms, and then they say, well, there's all kinds of like utility functions that fit these axioms, but we're going to assume ours is well behaved, which means like when we put it into another like model, we can actually maximize it. So like a utility curve that goes like that wiggles, that technically does fit like the axioms that such that preferences are well ordered, but the whole function is not well behaved, meaning we can like actually do the math with it that we want to do, which is, so like you could have a constraint that's tangent to the indifference curve in multiple spots, such that one choice is like the output of the model. Like there's a set of parameters, like the prices and your income or other actions of other people or something like that, and then one choice, like the maximization, is the output of that model. That's that takes these other assumptions as well. So it might be, if the question is, can we propose, can these axioms in economics, it would be complete if every single utility function that we propose could generate a choice, like when we put it into the model. That would be incomplete unless the function is not only well defined but well behaved, which is another set of assumptions I guess you have to add in, which are reasonable, but they are assumptions.
We can certainly add on like other conditions onto the behavior of a utility function and ensure that we'll have, like, you know, solutions and to it. here's another example, maybe, right? And this is a little afield from like utility function microeconomic, like, principles, but a time value of money equation. If one wants to find the internal rate of return on an investment, this is basically, and the internal rate of return is the interest rate, or the required rate of return that an investor would have to receive in order to be just indifferent between taking on or not taking on some new investment. So what that looks like algebraically is you'll have like the price of some asset on the left-hand side of the equation, and then you'll have a sum of discounted cash flows on the right-hand side. And that sum of discounted cash flows on the right-hand side is a polynomial of the same order as the number of time periods that the cash flows are coming. So right, so like an nth order polynomial, and the internal rate of return is basically
just to be clear, that means that, so say like you see the first period is discounted by j, some number between 0 and 1, and the second period would be discounted by j squared, and the third period discounted by j cubed, and that ensures that you have time consistent preferences.
Yes, yeah, we're just saying that the guy is going to that the price of this asset will basically converge to the sum of discounted cash flows, because people care about people discount the future, right? So it's just capturing that, right? Yeah, so it'll be like if cash flow 1 maybe is going to be divided by 1 plus x, where x is this discount rate, and then for the first period, and then period 2 we'll add cash flow 2 divided by 1 plus x squared, like all of 1 plus x is squared. So the discount rate will compound just as you're describing. You'll square it and then cube it, and then just and my point is just that there are n solutions to that equation, and many of them are complex, and it's like you'll have, but like what do those mean? And actually, and like and this is kind of like a pet like interest of mine, because there's a book on my bookshelf called Multiple Interest Rate Analysis. I'm actually like particularly interested in complex analysis related to economics and finance, like applications of, but like, so that's like, but in general, like, yeah, I think that yes, or maybe I'll just kind of put this out there as maybe it's an assumption I'm making, but that the Gödel's theorems may be applicable in some ways to economics and economic theory. Ideas about incompleteness might be applicable to economic theory, especially if one is trying to, come up with a central plan, a system that tells you what to produce and what not to produce. In the whole global economy, might be kind of a fool's errand if you have to come up with a but that's a real big political spin on this book that's not there at all in the text, probably.
The text is concerned with an interesting but yeah, very different problem, which is, as I understood it, what his fundamental motivation is, Hofstadter's trying to explore how it is that consciousness emerges from something that's not conscious, or something seemingly not conscious. And he says that it gets explained, and he doesn't say yet how it gets explained, but he says it gets explained by this idea of strange loops, which occurs where you have a system that generates emergent properties, which then affect the system, which affects the emergent properties, and so on in this kind of infinite spiral. And his like 3 examples of it to start out with, to get you thinking about this idea of strange loops, are Escher paintings and Bach fugues and Gödel's theorem. That's what I understand, like the general plan of the work to be. Do you guys have the same kind of impression there?
Yeah, it seems to be primarily about Gödel's theorem, or that's how he phrased it. That it's at its heart, the ideas are about Gödel's theorem, but Escher and Bach are like the primary illustrations of it.
Yeah.
Right.
What's the difference between the first part of the book and the second part of the book? Maybe the first part of the book, he's going to focus on Gödel's theorem and how that produces things. And then the second part, I don't know, maybe he's going to go back into specific examples.
Because the first part is called GEB and the second part is called EGB.
Right.
Oh yeah,
Eternal
actually,
Love
just
and
from
Grace.
looking at the chapter titles, that's what it looks like it is. The second half is about brains and mind and
Okay.
stuff like that. Okay, cool.
Mhm.
But yeah, that's probably what it is.
Oh, that's neat.
Yeah.
Very cool.
Yeah, I'm also really interested in there's an essay that I've talked to Tegan about by William James. I can't do anything without bringing up at least one William James essay. It's called Reflex, Action, and Theism is the name of the essay. And I forget exactly what the whole of it is about, but it's got this really interesting thing right at the beginning where he's talking about right after Darwin comes out, everyone is like coming up with all kinds of theories, and someone's like, oh yeah, what if like all behavior is like reflexes, right? So if I see fire, it will help me survive and reproduce to not jump into the fire, but it would also help me to survive and reproduce to use it to like feed my family or something like that, right? Like to cook food and feed my family, and then we get big brains because we don't need a digestive system and that kind of stuff, right? So then like since that is makes me fit in the environment better, I'll develop these, or my ancestors were selected for having reflexes which makes them not touch fire but knows how to react around it, so that the other thing that they want to eat, that food, they don't like it when it's raw, but they like it when it's cooked with fire. And these are all like reflexes. They're all like hitting your knee and having it bounce at the doctor's office or something like that, right? And so then it all fits together, right? And so you don't even need a soul or something like that. So your brain is just like a complex web of all of these inherited reactions to things. And then maybe like there's a circuit in there for like collecting new things. Like I see your face for the first time. Like my ancestors never saw your face, but I see your face and then I associate that with things in the past. So I react to you in this way or that way, depending on our relationship during my actual life. But then James says, okay, that's all interesting and stuff. And it's an interesting application of Darwin's theorem. But the big problem that you have to explain is consciousness, right? Because if that's the case, that everything is a reflex, then there's no need to choose ever. There's no need to be in a situation and then to have like some kind of self-awareness of what's going on so that you can select or something like that. You could just be dead matter. You could be like a robot or something like that. So consciousness wouldn't make sense to evolve something like that if you could summarize all that you need to do to survive within just a complex set of reflexes, like a set of rules, basically. So I imagine this is kind of where it's going, which is just something like you can't summarize all of action and reaction, you can't summarize all action as reaction, right? So you need this other element, which is acting outside the system, which is something that human minds have that computers don't have. But then the question that AI researchers are trying to do is say, can we put that in? That's the question.
And that's what he was doing a little bit with this MIU puzzle. He was saying, there's the mechanical part where you can just try a lot of things, but then there's the intelligence part, or maybe the intuitive part, where you try to see the pattern from outside, and that's what you're talking about. Thinking that's not just what reaction or reflex. Is it possible that there's something just beyond simple reflexes that's really thinking and consciousness? I think you're right. That's where he's going.
I think there's a couple quotes that could speak to this too. Like on page 26, sort of after there's an indented quotation, but then the paragraph after that, here one runs up against a seeming paradox. Computers, by their very nature, are the most inflexible, desireless, rule-following of beasts. Fast though they may be, they are nonetheless the epitome of unconsciousness. How then can intelligent behavior be programmed? Isn't this the most blatant of contradictions in terms? One of the major theses of this book is that it is not a contradiction at all. One of the major purposes of this book is to urge each reader to confront the apparent contradiction head on, to savor it, to turn it over, to take it apart, and to wallow in it, so that in the end, the reader might emerge with new insights into the seemingly unbreachable gulf between the formal and the informal, the animate and the inanimate, the flexible and the inflexible. And the contradiction that he is talking about is this this paradox about basically like computational and understandings of intelligence.
A long time ago, I can't even remember when. I remember I was talking with someone about having computers playing chess. This is 30 years ago, maybe all earlier, and it was very strange. The person said computers can never play chess that well because they don't have creativity. Okay, well, now here we are today where computers are really playing better chess than most humans, and they're making moves that appear to be creative, even though we kind of know that they can't be creative. They're kind of mechanical. So at what point, where is the dividing line that says something is just mechanical and when it becomes creative? I think that's where he's getting at here too. It's a very fuzzy line.
I guess it's actually, it might not be too hard to code something to appear creative, but we know that there's something different about being creative. So if in chess, there's only so many moves it can do, so the computer can observe like all the moves that have been played before and say like, what's the one that has been played the least, but isn't proven to be like a bad move, and then like do that or something like that. So it's because from the outside, the appearance of creativity is just something new, right? But to create is an inside experience, right? Or it's something that you can only perceive from the inside. So, and that it also doesn't mean that none of this or all of this stuff, which is very interesting, obviously, is not to say that in a foot race or something like that, mechanical systems can't outperform creative systems. Because creative systems doesn't actually mean they're right. You could be like, you could create like, you can make bad moves within the formal math system. Or if you're trying to make, like, let's say, like if we're trying to make economics totally fit the way that humans act as like a formal rule system for how to model isomorphically how humans act, we might say, oh, well, let's add in this thing called creativity, where just like we get to like say choose everything they do, then the system starts to like break down, which is what really the debate in like Austrian economics over whether or not you should put entrepreneurship in the model is all about. Because as soon as you do, then you basically let go in a way, and like, and you let go, and you give up the ability to like control everything inside.
Going back to the oh, sorry, go ahead.
Well, just quickly about creativity. There's creativity just kind of means doing something different. And the problem is doing something different isn't always good. Although I think a lot of people do think so. And I think he's going to get back to that in later chapters. He talks about John Cage later on, right? John Cage was someone who was very creative, although some people will question whether it was any good or not. Okay, but I'll go there. Tegan.
Yeah, I was going to say, going back to the discussion about chess computers, maybe one way to get at the difference between the kinds of creativity that are going on there, or the creativity in the human mind versus the absence of it in the AI mind, is in looking at the different rates or speeds at which humans come to appreciate positions relative to artificial intelligence. So AI smokes humans on chess tactics. you can get, because what an AI does is it just looks at all possible board states for a series of certain number of moves ahead, and then backwards inducts to the best position, where the best is given by some kind of exogenous criteria that the programmers initially decide for it. And it's usually like a vast set of different criteria that have different weights that the computer's optimizing. And so you get a computer that can just look 2 moves into the future, and it just crunches all the board states back, and it will achieve a rating of like 1670 or so, which is like not bad at all. Like that's not like grandmaster level, but he's just looking 2 moves ahead. So now the very best computers, they look like 300 moves ahead or whatever. Like you just have massive amounts of computing power behind it, and they can just smoke everyone because they can look at so many different possible board states. But it's only very recently that we've come to have that level of computing power. And so for a very long time, there were openings that were widely regarded as some of the very best, most interesting, most creative kind of openings played by grandmasters that computers routinely evaluated as very bad because they couldn't crunch that many positions into the future. And yet humans continued to play them because we were able to recognize that these openings were in fact good. They secured positional advantages that did come up so many moves in the future. They would the advantage would only materialize in the end game. Now that we have computers that are able to look that far ahead, it turns out the grandmasters who are playing these initially have been validated. And yet the grandmasters got that knowledge not by doing this crunchy backwards induction, but by some kind of insight into the way that the board and the pieces work and interact together. And so it's not in the move itself that the difference becomes apparent, but instead in the way by which humans come to understand those moves as good. Chess masters are doing something fundamentally different than computers, and yet are reaching the same conclusions about positional advantages now that computers have caught up to human strength.
There's a quotation that like dovetails really nicely with what you just said, Tegan. On page 36, it says this sort of a second paragraph after the inside and outside the system. Even if a person is not very bright, he still cannot help making some observations about what he is doing, and these observations give him good insight into the task, insight which the computer program, as we have described it, lacks. Now, let me be very explicit about what I mean. What I mean by saying this shows a difference between people and machines. I mean that it is possible to program a machine to do a routine task in such a way that the machine will never notice even the most obvious facts about what it is doing. But it is inherent in human consciousness to notice some facts about the things which one is doing. But you knew this all along. If I punch 1 into an adding machine and then add 1 to it and then add 1 again and again and continue going on doing so for hours and hours, the machine will never learn to anticipate you and do it itself, although one person would pick up the repetitive behavior very quickly. And then sort of later on, but so he's also not saying that all people are always making sophisticated observations, picking up on the quotation. People, in fact, are often very unobservant, but machines can be made to be totally unobservant, and people cannot. And this is so like this I think there's like a distinction between creativity as like combinatorial like execution and recognition and cognizance necessary for human consciousness. And I do think that like it's worth mentioning Kerzner, who his entrepreneur is an entrepreneur who discovers arbitrage opportunities. And it's not so much, and he emphasizes in competition and entrepreneurship that like it's not so much the ability to execute or who's bearing the risk or what, but it's this sort of ability to notice and discover that Kerzner anyway emphasizes.
I think that's one of the things. I think Kerzner is great. I love Kerzner, especially that book. But I think that's one of the things that makes it hard to read what he's saying, because obviously an entrepreneur is not going to be able to build. When I think of an entrepreneur, I think of somebody that starts a business, right? That's the colloquial meaning of the term, right? And if somebody has no capital, they're just naked on the sidewalk and they go, dang, that would be a great business right there. No one would call that guy an entrepreneur. But what Kerzner is saying is he's he's filing down to the essence of what makes something an entrepreneur, someone an entrepreneur. So somebody who's just like, yeah, I already know, and everybody knows that this is a good investment, and just puts their capital in a way, they're of course entering into the market. But Kerzner is trying to isolate what makes entrepreneurship an essential quality of what makes a market function. That's why he focuses on that to the exclusion of everything else, right?
And it's worth stating, just maybe but like, you know, there's a lot of different like theories and definitions of entrepreneurship, and you know, like just so you know, some others are like the Schumpeterian entrepreneur is sort of this archetypal innovator, you know, and you know, other people, you know, sort of identify ownership with or management decision making with entrepreneurship. But yeah, Kerzner even says like, well, the owners and investors in a firm don't even have to be the entrepreneurs. They could contract that out to like an entrepreneur whose duty is like, and not duty, but whose you know, value added or what they're specializing in is the mere like identification and, you know, noticing capacity of. But yeah, but that relates to this text. I mean, you know, because it's this noticing that maybe distinguishes computers from human intelligence.
Or is the entrepreneur the one person who already has a concept, like I said, a mental concept of what's the best thing to do, that's sort of outside everybody else, that nobody else sees. And so there's a lot of failed entrepreneurs, because a lot of people think they know what they're doing, and they do something completely wrong. So, or that doesn't succeed in the marketplace, so to speak.
And just as somebody could be executing a task, you know, somebody could be executing a task and noticing totally incorrect patterns and making false statements or whatever in the system, or giving the wrong answers to whatever the task or question is, but they're doing something different than a computer does in that process.
I remember in high school, this is when we had fairly primitive computing machines, and there was a process on one of the machines, and they just said, well, the output from this is basically a random number. And my friend, who was, you know, really smart guy, he eventually figured out how this process worked and could predict what the random number was going to be. It was after some operation like a square root or a special division or something. But he, seeing through all the things, thought out all the possibilities and figured out why it really wasn't a random number, and figured out what the random number was going to be. It was a remainder from a certain operation or something like that. It was so like I said, he saw it through it. He was like the entrepreneur in that situation. Everybody else, well, we just think it's a random number.
That's cool.
Yeah, I think, and that's why those things are why it's so hard to model an entrepreneur or to build a complete model of something like that. Because if you think of, this is why Kerzner emphasizes like product differentiation and stuff like that. So if you think of like a mathematical model of the different qualities of a product, you might say like there's some spectrum from 0 to 1, and then consumers are distributed with preferences across that spectrum somehow, and then producers decide to like capture different sections of the market by making their products slightly different, right? And then when you have a model like that, and then you know that everyone else is operating with the same model, all the arbitrage opportunities disappear quite quickly, or it's very hard to model how you like model it in any other way other than that they reach the one maximizing equilibrium. That's why, so the true entrepreneur is the one that realizes, oh, we're on this spectrum, but there's also another orthogonal like spectrum for this other quality of the product, that they're like, oh, well, people want like hats that like are like warm, not just like blue or whatever, you know. And so that they're always, but you always have to operate outside of that formal model to say something like that. So it's, yeah, that's basically good news, bad news for economics. And the good news that it's always going to be interesting. There's always going to be interesting things happening in the economy, but bad news is that we can't like predict them all 100% or declare like efficiency conditions for them or something like that.
Polanyi makes that point about the scientific discovery and scientific inquiry in several places in a lot of his writings, and that's why he argues that research universities with certain kinds of pedigrees are actually super important to the scientific process, and you can't just import like the kinds of fancy research gear that they have at physics labs somewhere else to now a new location, because it's not just how much funding they have, it's not how much gear and research equipment that they have, but there's this tacit transmission of knowledge, specifically the skill of noticing problems, of noticing what solutions might be, of just noticing those patterns in whatever kind of research that you're doing. That is an extremely personal thing. And so it has to be passed on, communicated in this master apprentice style relationship. And research thus can't merely be a function of the amount of money that you throw at it or something like that, which obviously has huge implications for capital theory in economics, right? Like if your idea is to get development in the third world, you can't just give them lots of money. If this model of understanding reality is true and actually does apply, you can't just give a bunch of money, you can't just ship a bunch of gear or whatever over there. There has to be some kind of training and insight in the way to think. You have to have entrepreneurs who gain that capacity to notice.
Yeah, some selection for actually useful capital inputs that would be complementary to the existing capital in that location, with the labor, the state of labor in that, so how specialized it is, how, yeah, I mean, it requires a lot more on the ground local tacit knowledge than than plopping a bunch of money in one. I mean, I think anybody who would have enough knowledge on the ground to make a really a real optimal decision in that, or an efficiency enhancing decision in that society probably wouldn't even come up with plop a bunch of money on this place. They'd have a much more kind of, anyway.
Or the ones that do, they usually have some other goal with that money in mind. So they'll say, yeah, dump a bunch of money on us, and they end up using it for something else. So they hijack the hubris of the other system or something like that. Yeah. I guess we could wrap it up there. We've gone about an hour, and we want to save stuff for other weeks too. So yeah, unless anyone has final thoughts on this.
I have one thing which I noticed, which is a little out of left field, but can any of you connect these four chapters that we read to Bob Newhart?
I don't know who Bob Newhart is.
You don't even know who Bob Newhart is?
No.
Was he in the Mary Tyler Moore Show?
No.
I don't know who Bob Newhart is.
He had his own television show in the 80s called The Bob Newhart Show, and then a later one called Newhart, kind of in the 90s, early 2000s. He was a comedian. And the third chapter of this book, the second part, the dialogue, which is, what is it? Something for Achilles only, right?
Yeah, the Achilles phone call.
All right.
Sonata for unaccompanied Achilles.
Right. Guess what? Bob Newhart's trademark skill when he first came out in the 60s was the one-sided telephone call. And he even had an album, you can look it up, called The Button-Down Mind of Bob Newhart. And it's a series of these phone calls. That was his trademark when he first started in comedy. And I actually noticed it in a movie once. There was a movie called Hell is for Heroes, starring Steve McQueen, but Bob Newhart was in the movie also, because it was a story about this camp in World War II where they knew where there were Germans on the other side of the ravine, so they were trying to make sure that the Germans thought that there were a lot of them there. So they took their Jeep and they redid the gears so it sounded like a big truck, and they kept driving it back and forth. And then they also set up a phone system so that Bob Newhart would do all these one-sided telephone calls. And they thought, oh, there's a bunch of people there talking with headquarters and everything. Interesting movie, but you might want to look that up. But that's what, when I first saw that, that's what it reminded me of. Bob Newhart and the one-sided telephone calls.
Cool.
Okay.
That could be, well, I guess this book came out before that then, right?
No, he was in the 60s. The book I
yeah.
have here is 1980 copyright.
Okay, yeah.
So he may have known about Bob Newhart, but I don't know. I didn't see him make the connection to Bob Newhart,
Right.
Unless it's in the footnotes.
Maybe
somewhere.
It's passive. You're supposed to think outside the system and notice the connection.
Yeah, is right. Okay.
Oh, and then the one last thing, we were talking about it before you came, but did you actually solve the MU puzzle, Matt?
I thought I did, but then I don't think I did, and I haven't gone back and checked.
Okay.
Like I thought I did at the time, and then he kind of kept writing about it, and I was like, oh, maybe it was more complicated than I thought. And then
yeah, I misunderstood rule 2 at the beginning, and then I did it in 2 steps, and then I looked back and I went, oh, that's not how it works at all. Yeah.
All right.
He says he's got a solution for it. What did he say? Like it's in chapter 8 or chapter 13 or something like that.
Yeah, I guess we'll get to it when we get to it. Yeah.
Yeah, I thought like you could add like I think that you could get the 3 I's and then replace that with a U after the M, but I must have misunderstood that. I think. I don't know.
Yeah. Well, but and for anyone listening to, it's definitely worth checking out the book and reading it along with us, because we cannot summarize the style of the book in just conversation. So
like the puzzle does a great, like the puzzle like serves a purpose, right? It's like the puzzle like demonstrates something about formal proof systems, which is like what do you need? You need like, let's bake the cake. You need some symbols, you need an axiom or 2, and you need some rules of inference, and based on those things you can tell whether something's a theorem or not.
It's a great little teaching example.
You could do a course on this book. Maybe like half a course on this book, maybe a course, probably actually, if you supplemented it with a lot of other
stuff. There's a course, one of the, I can't remember which Ivy League, it's like Princeton or Yale, one of them did, there's a course online that they did in like 2008, awesome. But you can like go watch all the recorded lectures.
Oh, awesome. Yeah, Yale does great courses like that they just put online. I'm watching their game theory course right now.
Nice.
Yeah. Okay, but I guess we'll wrap it up there. And next week we'll do chapters 4, 5, and 6.
Okay.
See you around.
Bye-bye.
Yes.
Bye.
Talking to you.